All right, it is time to talk about heat calculations, the problems. So what reference tables will you use? Okay, first of all, table B, physical constants for water. So here's my reference table. You can see right here, table B. Now, you don't have to remember this stuff for water. And honestly, you don't have to remember this stuff for anything. So if the substance in the question is not water, I have to give you this information, or you will be able to use the other information in the problem to calculate this, but you are not expected to memorize it for anything. Table D. So again, on the front of your reference table, but this time over here, table D, selected units. If you forget, what unit should I use for temperature? What is the unit for heat? What is the unit for time, volume, whatever? Forget it. Right here, table D. Table T, which has the formula for heat, well, 3 separate formulas actually, and then the formula for temperature conversions. So for heat calculations, you don't need to do temperature conversions. I just recommend it because then you don't have to worry about negatives. But again, so here we are, table T. We are at the back of the reference table, and you can see as we scroll down, the last two right here, okay, those are 2 things. So we have heat over here. We have 3 separate formulas, and then you are told what each individual thing stands for. So again, don't have to memorize it. Beautiful. All right, so we mentioned table D for units. So what units will we actually use? Well, for mass, it's most likely going to be grams, although it could be kilograms. You just have to be careful with the units for specific heat in that case. For temperature, can use degrees Celsius, can use degrees Kelvin. Remember, temperature is a measure of the average kinetic energy of the particles. I recommend using Kelvin because then you don't have to worry about the mistakes with negatives, but for the heat calculations, it is not required. Okay, what about heat? Well, remember, heat is thermal energy as it moves from warmer to colder objects. And usually we see heat in joules, but you can see it in calories or kilocalories. Although again, if you're using specific heat, the units for specific heat have to match up. So usually we're going to see joules, sometimes kilojoules, and then a few times you might see calories or kilocalories. All right, specific heat. What is specific heat? So specific heat is literally specific. It is the amount of heat it takes to raise the temperature of 1 gram of a substance 1 degrees Celsius. Specific, right? The specific heat of water, the specific heat capacity for water, remember, is on table A. So we can call it specific heat or specific heat capacity. For any other substance, you have to be given the specific heat, or it can be calculated from the formula. What about the calculations? Okay, so here's how to do temperature conversions. We've done this before. So if you're given a temperature in Celsius, you add 273. If you're given a temperature in Kelvin, you subtract 273. So when there is a temperature change, okay, so let me grab my pen here. So when there is a temperature change, you see this delta T stands for change in temperature, which would be the final temperature minus the starting temperature, okay, initial. It doesn't tell you that, so you have to know that piece, okay? So final minus initial. So we use this formula when there is a temperature change. What does C stand for? Specific heat capacity. What does M stand for? Mass. What does Q stand for? Heat. Don't have to guess it. The only thing you have to remember from your head is a change in temperature. It means final temperature minus initial. And it matters because our answer, whether it's negative or positive, will indicate exothermic or endothermic, okay? All right, now what if there is no temperature change? So you see here we have two formulas right here that don't include temperature. So we have one that has HF. What is that? Heat of fusion. Remember, that's melting or freezing. So if the substance is melting or freezing, we would use this formula right here. And what does HV stand for? Heat of vaporization. So right here, if the substance is vaporizing at its boiling point or condensing at its condensation point, which is the same temperature, then we would use this formula, because remember from heating and cooling curves that when a substance is changing phase during fusion, during vaporization, there is no temperature change. So if we had delta T here, it would be 0, and that would give us no heat, which would make no sense, okay? So when you look at your answer, again, the order of the temperature numbers matter. If you get a positive answer, it's endothermic, energy is absorbed. So that's anything that's on a heating curve. If you get a negative answer, it's exothermic, energy is released. So anything on a cooling curve. Remember, energy out, exothermic, energy in, endothermic, exothermic, endothermic, exothermic, endothermic. Exo is a cooling curve, endo is a heating curve. Okay, so this can apply to heating and cooling curves. So let's just do a brief review. So in what part of the curve would substance X have a definite shape and a definite volume? Well, that's a solid, so that's right here. In what part of the curve would substance X have definite volume but no definite shape? Well, that's a liquid right here. In what part of the curve would substance X have no definite shape or volume? Well, that's a gas. That would be up here. This section is melting solid, changing to liquid. So we have both states of matter. This section right here is liquid changing to gas, vaporization. We have both states of matter right there. What is the melting point of substance X? Well, here's where it's melting. We go across. It is 5 degrees Celsius. What is the boiling point? Here's where it's boiling. We go across. There we go. 55 degrees Celsius. So is this water? Negative. Water's boiling point would be 100 and water's freezing point would be 0. Okay, so now here's a question. Calculate the total heat energy in joules needed to convert 20 grams of substance X from negative 10 degrees Celsius to 5 degrees Celsius. Okay, so you can see negative 10 to 5. Okay, it would be just a solid at that point. So I need what formula? Q equals M C delta T. Remember, delta T is final minus initial. So temperature final minus temperature initial. So what was my final? 5. What was my initial? Minus 10. Do you see why converting to Kelvin might be helpful? Okay, but a minus gives me a plus. So this temperature change is 15, okay, degrees Celsius. All right, so my mass is 20. Oops, hold on. No, 20 grams. My C, specific heat of the solid, so I need this one, 2.0 joules per gram. Degrees Celsius means it is on the bottom, times my temperature change, which was 15 degrees Celsius. So what cancels out? Degrees Celsius, grams, grams. I'm left with joules. So I do this. 20 times 2 Okay, so that's 40 times 15. For you on here. 20 times 2.0, so that's first, times 15. Okay, so that is the whole problem, equals, so my answer is 600. 600 what? No naked numbers, joules. Okay, there we go. So we can use this information when we get heating and cooling curve questions. And that's it. That's heat calculations. I hope you learned something new today.